and what's up to you all grade 10 mindsetters? My name is Abram and I'm ready to learn more and learn extra with you guys doing physical sciences. And today we are with Tracy, of course. Tracy, how are you?
I'm very well, thanks, Abram. How are you?
I'm doing well. Thanks. It's been a good Tuesday. I cannot complain. You're so glowing, hey?
Oh, thank you, Abram.
Tell you what, I noticed something that probably other mindsetters don't notice, but I do notice. There's like a third member in the studio.
There is another person in studio with us. Very exciting mindsetters. I've got an announcement to make. Very exciting. I am pregnant with my first little baby.
Oh,
and,
nice.
Very, very exciting.
Is it a boy or girl?
It's a little girl, is what we've been told. So we can't wait to have her in July. And we're just so over the moon. My husband and I are so excited to have our first child and to grow our family. So that's the big exciting news. I'm 27 weeks pregnant.
You know, this is our first Learn Extra baby, hey?
First Learn Extra baby. Well, I'm hoping she's not going to arrive when we're in studio.
No.
Of course not.
But she's going to be our angel. Tell you what,
will.
babies are just a blessing from God. And whenever you bring a new baby, I mean, it's an excitement and joy for the entire family and the whole world.
Absolutely. And it's such a blessing from God. We're really so delighted. And I know she's going to bring lots of joy and excitement to our family. She's our first grandchild on both sets of families.
Wow.
So both my parents and my husband's parents. So we can't wait.
Awesome. And
congratulations
once more again,
Tracy.
Tracy.
Thank you so much.
Well, we're going to see more of what Tracy's going on.
And you will see this bump growing.
We'll keep you in track. We'll keep you in track. But today, to your kids, your wonderful old kids, what are we doing with them?
So, mindsetters, we've got lots in store today. We're going to be looking at electromagnetic radiation. And if we look across, electromagnetic radiation is how we communicate hugely. So, we're going to be discussing electromagnetic radiation, defining it and discussing it significantly, and doing lots of calculations with the energy of photons and all that kind of stuff. So, lots in store for today.
Nice one. Talking about lots of things in store, we have an awesome competition for you mindsetters. It is a giveaway of a Casio calculator, proudly sponsored by Casio. So all you need to do is to download your notes or view your notes and then go to the test yourself questions. The link is provided on Facebook for you. Fill in the form. You have up until tomorrow at 4 p.m. to submit your right answers. So we'll be waiting to get those right answers, but we also have the challenge question. So many things are happening. Good stuff though. The links are on facebook.com/LearnExtra. You can also follow us on Twitter @LearnExtra. Keep your questions coming through as Tracy's going over the questions. Otherwise, back to you, Tracy.
Thanks so much, Abram. So mindsetters, I've got some really interesting challenge questions and lots of interesting test yourself questions too. Please go and really do challenge yourself and engage and participate with us. Let's look through electromagnetic radiation. In this lesson today, we will obviously define electromagnetic radiation. It's always important to have some kind of base point to define it. We will identify various uses for the various ranges of electromagnetic radiation. We're going to do some questions, and so we'll solve for frequency and wavelength using the wave equation, and then also we will consider energy and calculate the energy of a photon. So there's lots in store, and I think I should get into the challenge question for you, so you can go start thinking about that challenge question and post your answers on that Facebook link. The challenge question. So a roving lunar module. Lunar is referring to the moon. So this is some kind of spacecraft they've put up on the moon, and it's moving around and it's communicating with a NASA spacecraft. Okay, so that lunar module is communicating with a NASA spacecraft which is orbiting above the surface of the moon at a height of 8,000 kilometers above the surface of the moon. The lunar module emits a pulse every 5 seconds, lasting 5 seconds, and that pulse happens every 15 seconds. The frequency of the pulse changes from it starts low frequency and goes across to a high frequency continually. So the frequency of that pulse is changing. And I've got 3 questions linked to that information. How long would it take for the radio pulse to travel from the lunar module to the receiver of the spacecraft. So this lunar module is emitting a pulse up to some spacecraft that is orbiting with the moon. How long would it take for a radio pulse to travel from the surface of the moon, where that lunar spacecraft is, that lunar module is, across to the spacecraft? Suggest why it might emit pulses of different frequencies. Notice it was going from a low frequency changing to a high frequency. Why would that be? And then part C of this question, would there be any difference in the time that it takes a high frequency pulse to travel compared to a low frequency pulse? And there you're thinking about how long would it take in terms of a high frequency pulse or a low frequency pulse, and the question is there for you. So three parts to that question, lots to get through. So do challenge yourself and think through those questions. Draw it out is my first suggestion. Surface of the moon, the spacecraft, write up as much information as possible. Okay? And do challenge yourself, participate with us. If we turn to do a quick summary of electromagnetic radiation, we're considering electromagnetic radiation is part of a whole spectrum of radiation, and our eyes can only detect a small part of that spectrum. Our eyes can detect visible light only, and that's just a very, very small part of this continuous spectrum. And we use various parts of that spectrum for different uses. Radio waves, microwaves in our microwave ovens, infrared radiation, visible light we can see, ultraviolet lights, X-rays, gamma rays are all part of this entire electromagnetic spectrum, which is very, very useful. So, visible light is only a small part of a whole range of radiation that our eyes can't detect. But it is a very useful spectrum. Now, what is electromagnetic radiation? Well, it's made up of changing electric and magnetic fields. And when this was discovered, it's very interesting because people used to think that electricity and magnetism were completely separate. But actually, we've now discovered that an electric field causes a changing magnetic field, and a changing magnetic field causes a changing electric field. These two, what we thought were separate, are actually quite closely linked. And so, and the way it was discovered was through a whole study of electrodynamics or electromagnetism. It's an amazing section of work. And so what happens is that if you have a charged particle, so an electric charge, and it accelerates, it sets up a changing electric field, and that in turn sets up a changing magnetic field. And then the changing magnetic field sets up a changing electric field. And so these two fields are interacting with one another all the time. And that's incredibly useful. So if you'll notice here, on this graph, I've got two fields. The vertical dimension in this diagram is representing the electric field. You notice that's an E there. The horizontal field coming out the page at us is represented by that B, which is representing the magnetic field. So these two fields interacting, and as the one changes, up, down, the other one changes left, right, left, right. So they're at 90 degrees or perpendicular to one another. Incredibly useful, because what it's going to mean is that because it's changing fields, it's actually meaning that it's not going to need anything to propagate through. It's not going to need a medium through which to move. So if we turn to some of the properties of this electromagnetic radiation, is that they travel at a constant speed. So all electromagnetic waves, or all electromagnetic radiation, travels at a constant speed, and that constant speed is specifically in a vacuum at 300 million meters in every second. Okay, so that's incredibly fast. The speed of light, you might have heard of, can't break the speed of light. Well, who knows? But the reality is that here, this is an incredibly fast speed, and see my meters per second is on the other side here. But notice when we deal with very big numbers, they can be quite cumbersome to work with. I mean, if you dropped off a naught by mistake as you were writing down this number, it would make a big difference. And so usually we work with scientific notation when we deal with, in science, very big numbers, or very small numbers. And so you'll notice I've converted this to a speed as 3 times 10 to the power of 8 meters in every second. That's in a vacuum, and that's a constant speed for all electromagnetic radiation, whether it's a radio wave, a gamma ray, an X-ray, across the board, visible light, all of those travel at the same speed in a vacuum. The other issue I've already mentioned is that it does not require a medium for electromagnetic radiation to pass through. And scientists have debated this for a number of years, specifically because they thought, well, what is light? Is light a particle? Is light a wave? And they had various different arguments. And most waves require a medium to pass through. So if you think about transverse waves, when we looked at waves through a slinky or a coil or a rope, that's the particles of the medium would be the slinky or the rope. If we look at water waves, the water is the substance through which this wave is passing through. If you think about sound waves, sound is traveling through the air particles surrounding us, or obviously through any other substance that it is able to pass through. In comparison, this electromagnetic wave, because it's changing fields, it doesn't require a medium to pass through, and that's critical. So, this issue, no medium is required for electromagnetic radiation to pass through. And then the next point, the wave-particle duality. Now, I mentioned scientists have struggled with this thing. Is light a wave or is light a particle? And there actually is evidence for both. So, if we're investigating something like interference of light, you can shine 2 spotlights onto maybe the school stage, and they would add together and make a bigger spotlight, a bigger, brighter light at that point. There would be interference. If you were discussing, so you'd have constructive and destructive interference. If you were discussing, well, that's a wave nature, isn't it? Because you've had constructive and destructive interference in waves. But there is other evidence that light acts as a particle, and this is based on the photoelectric effect, which is something that Einstein did a paper on and got a Nobel Prize for. Something we'll do in grade 12 if you continue with science, a very, very useful factor. But the wave-particle duality, that light can, and all EM radiation, acts both as a wave and as a particle simultaneously. We would only see one or the other in terms of its properties depending on the experiment we're doing. Okay? So only one would be investigated at a time, but notice that all EM radiation is 100% a wave and it's 100% a particle. It's got this duality. Then I've got a picture that represents the various this whole spectrum, and I want you to focus on this squiggly line, okay, because that's indicating the radiation. And notice we're going from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays are all part of this continuous spectrum. And it's helpful that we have we've got different names for the different ranges of radiation, but it's continuous. There's no gaps, there's no kind of holes in it. It's a continuous spectrum. And I want you to notice that radio waves have long wavelengths, okay? They cover distances. Notice a wavelength of 10 to the power of 3, so 1,000 meters, okay? Whereas gamma rays have wavelengths that are very, 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 very tiny, times 10 to the power of negative 12, so a very small wavelength, but high frequencies. And so through this whole spectrum, we have different uses for different parts of the spectrum, and it's important that you go and identify those uses, and we can discuss how we would use, say, gamma rays, which are very dangerous, but could be used to sterilize equipment. Or we could discuss infrared radiation, which is the radiation given off by our bodies in terms of its heat, can be used in terms of various types of infrared glasses that you could detect a person moving with infrared glasses. Radio waves are used in terms of our communication systems, and so we could continue. Now, having a look at that type of picture, recognize it's a whole spectrum and the different uses of each. And that's, I think, very important that we start with that. When we come back from our short break, we're going to discuss some questions that link to this electromagnetic spectrum. Abram, over to you.
Thank you so much, and so many messages for you saying congratulations to the Mindsetters. Are so thrilled as much as we are, hey?
Thank you so much, all the Mindsetters. I really appreciate that.
Thank you for the love and support, Mindsetters. Well, you've got so much to do during this break. The challenge question is on facebook.com/LearnExtra. Follow us on Twitter @LearnExtra, and make sure that you keep your answers coming on the Test Yourself questions that are on the form that is provided on Facebook in order to stand a chance of winning this awesome Casio calculator. But for now, we'll check you out after the break. Welcome back, Mindsetters. Now we have a help desk that is there to help you guys. It's apps.facebook.com/LearnExtra help desk. But I am here on Facebook. If you're struggling and have some questions, I'm here, and Tracy is going to answer those questions. In the meantime, you also have the challenge questions. So give it a try, and we'll see your answers later on. Tracy?
Thank you so much. And Abram, I really wanted to encourage the Mindsetters to practice and try some of those questions, and specifically into that competition for Casio, because as you're going to see now, as science teachers, and science students, we use the calculators, scientific calculators all the time, and I think it's very important for you to have a scientific calculator. Specifically, the button that I want to show you, we're going to be using now, is this one down at the bottom here. Do you see it? It says the times 10 to the power of. And that's very helpful on a scientific calculator, because what it's going to do, we're going to be looking at, remember I said very big numbers and very small numbers. And what it's going to help you to do is just press one button instead of 3 or 4 or 5 or however many, to get you into scientific notation very quickly. So you don't have to press the times button. You don't have to press the 1 and the 0 to get the times 10, and then you don't have to go up to a power of. You can just literally, so if I'm writing the speed of light, or the speed of EM radiation, which is 3 times 10 to the power of 8. And so it's very quick in terms of working out very large numbers and very small numbers. So I do encourage you, Mindsetters.
Awesome. So Casio calculator is the best calculator, trust me.
Well, so useful.
Simplifying everything.
So useful. And so we're going to be using it in this question, and so I thought I'd specifically highlight that to you. So let's get going. 2 forms of radiation are given. EM radiation with a frequency of 0.5 T hertz. Well, what is that T standing for? That T is standing for terahertz. And you might have heard of maybe a terabyte in terms of kind of computers. Tera is standing for a very large number. The tera stands for times 10 to the power of 12. Remember I said we're going to deal with big numbers. And the hertz is the unit for frequency. EM radiation, another form of radiation, B, EM radiation with a wavelength of 890 micrometers. Notice a wavelength is a distance measurement, and they're giving this micro symbol, and micro stands for times 10 to the power of -6. So that's a very small distance. Okay? Calculate the energy of a photon of each form of EM radiation. So I'm going to do them separately. We'll start off with A, and I was working in blue. So A, I'm going to work energy is equal to H times F. That's the energy of a photon, and the H there is standing for Planck's constant, which is 6,63 times 10 to the -34. I'm putting that in brackets, and then the frequency was 0.5 terahertz. So 0.5 times 10 to the power of 12. Okay? So critical that you know what those prefixes mean, these little subunits. Okay? Now I'm going to go across to my calculator, and we can write those in. 6.63, immediately the times 10 to the button, and it's -34, multiplied by, and I'm going to actually just put this in brackets, so let's zoom across to the, if it will let me. going to clear it and do it again. 6.63 times 10 to the negative 34, close brackets, multiplied by, and it was 0.5 times 10 to the power of 12, close brackets, equals. There's my answer, 3.3. I'm going to round off to 3.32 times 10 to the negative 22. And notice it's giving you your answer in the scientific notation. So let's write it down in that scientific notation. And 3.32 times 10 to the power of negative 22. I'm just going to undo. Oh, maybe redo that. Or not. Sorry, I've jumped across. There we are, negative 22. Let's just try and clean that up and have it written easily here, negative 22, because I definitely want you to be able to see those that scientific notation. What's my unit going to be? Well, it's an energy value, so energy is measured in joules. The next one, B, and I think I'm going to do this towards the bottom of the page so that I've got some more space. And I'm going across to green. And B's answer was, well, it was also energy. And so you could say, well, I want to work with HF, but was I given the frequency? No, I wasn't. I was given the wavelength. So I'm going to write down wavelength. And I want you to identify that we can, and it was 890 micrometers, which is 890 times 10 to the power of negative 6 meters. I want you to notice that we have an equation that we can go straight into here. But the equation comes from somewhere. And the equation is based on the same equation. We have energy is equal to hc over lambda, which is the wavelength. Well, why is that? Well, the reason for that is because you may have come across C is equal to frequency times wavelength, okay, where notice this is velocity is equal to frequency times wavelength. We've had that many times in the last while as we've done waves and longitudinal waves and transverse waves. But the speed we're dealing with here is the speed of light, the speed of all electromagnetic radiation. So we've given it the symbol C, which is 3 times 10 to the power of 8 meters per second in a vacuum. And so what I'm actually doing is I'm rearranging this equation and I'm solving for F. Okay? So if I'm solving for F, it would be C divided by wavelength would give me the frequency. So coming across here, I've actually got the exact same equation as is written there, but instead of writing F, I'm writing, well, let's just take this part away so that you can see where we're coming with it. H times, not frequency, but C divided by wavelength, which I can write simply as one quick equation and write that as hc over lambda. So substituting in, we've got very quickly 6.63 times 10 to the negative 34. The C I said was the speed of light, or the speed of all electromagnetic radiation, which is 3 times 10 to the power of 8. And that's divided by the wavelength, which we'd written at the top here, was 890 times 10 to the negative 6 meters. Notice how important being able to write quick answers in scientific notation is going to be here. So cross to our calculator. I'm going to clear this answer. 6.63 times 10 to the negative 34. Multiply that by, it was the speed of light, 3 times 10 to the power of 8. I'm going to do my top line first, and that whole thing would be divided by 890 times 10 to the power of negative 6. and I get my answer 2,23 times 10 to the power of negative 22. Although we've got all these other digits, I'm going to round off to the second decimal place. So 2,23 times 10 to the negative 22. And going back here, it was 2,23 times 10 to the negative 22, my units, joules. So I think we've answered A. Calculate the energy of a photon. We have indeed. That's done. The next one, part B, compare the forms of radiation in terms of which has the longer wavelength. So when we speak about wavelength, recall we're dealing with the distance of one complete wave. Okay? And as you consider the distance of one complete wave, you're thinking through things like, well, what is its energy, what is its frequency? Those can certainly help you. And a quick thought here is high energy is going to always have high frequency. And because these things are related based on the C is equal to frequency times wavelength, the speed of light is constant, so that C is staying the same. The frequency, if the frequency is high, the wavelength must be low, or the wavelength must be short, would be a better word to use. So looking at it, I can immediately, just by looking at the energy, say which one has a higher energy. The one with high energy is going to have high frequency and therefore short wavelength. So quickly looking at it, what were my answers? This one was high energy, okay, and so I could say here, therefore, high frequency, low wavelength, okay. Which one has the longer wavelength? It must be this one, B, and you could work that out, okay. How could you work it out if you really wanted to? This one, we were given the wavelength, B's wavelength, and so I could go back and work out the wavelength here would be wavelength is equal to C over the frequency. So I could go and work that out, and it would be 3 times 10 to the power of 8 divided by 0.5 times 10 to the power of 12 terahertz. And we can get our answer. So 3 times 10 to the power of 8 divided by 0.5 times 10 to the power of, was it positive 12. So 3 times 10 to the power of 8 divided by 0.5 times 10 to the power of 12. And that gives me an answer which is 0.30. 0.0006 meters. And so you could go and compare that in terms of its wavelength, because remember that was the other wavelength. So you can compare them. Let's turn to our next question. We'll see how we go with this. I'm just going to clear these scribbles. X-rays, also part of the whole electromagnetic spectrum. It is given that the wavelength of certain X-rays is 2,3 nanometers. Now immediately I'm writing there, wavelength is equal to 2.3 times 10 to the power of negative 9 meters. Remember, very important that you go and learn what those little values are referring to. Nanometers, terabytes, tera, etc. Calculate the frequency of the X-rays. Now I've done a similar question a moment ago. We have C is equal to frequency times lambda. I always write the original equation first, and then you can go and play with it. What have I got? I'm trying to find frequency. So frequency is by itself is going to be equal to, well, speed of light divided by the wavelength. And that's 3 times 10 to the power of 8 divided by 2.3 times 10 to the power of negative 9. Now, I want you to note that negative is important, is equal to. So, calculator. Again, we're using this scientific notation. 3 times 10 to the button, power of 8, divided by 2.3 times 10 to the power of negative 9 equals. That's my wavelength, that's my frequency, sorry. 1,30 times 10 to the negative, times 10 to the positive 17. So 1.30 times 10 to the positive 17, and the unit here would be hertz. Okay. Now recognize that that's, and I always try and do this, recognize that that's quite a high value, and X-rays do have high energy. That's how they have such an interesting penetrating ability. Determine the energy of a photon of this X-ray radiation. Well, once again, E is equal to H times frequency. That was 6.63 times 10 to the negative 34. Multiply that by my answer previously, 1.30 times 10 to the 17. And I can get my answer. Calculator, 6.63 times 10 to the negative 34. Multiply that by 1.30 times 10 to the 17 equals, and we get our answer here as 8.62. 8.62 times 10 to the negative 17, and it would be joules. Check it quickly. 8.62 times 10 to the negative 17 joules. Good. And that's part B. Suggest a medical use for X-rays. Now I'm just going to answer this, I'm not going to write it down specifically, but think through. X-rays we use to detect broken bones. If you break an arm or leg, you would go and have an X-ray, and the doctors would be able to diagnose that broken bone. So, broken bones can be detected. Okay. Discuss the penetrating ability of X-rays. X-rays can penetrate through our skin and through our muscle layers, but they can't penetrate through bone. So they can penetrate quite deep, but not through our bones, which is how we can detect broken bones. What precautions would medical personnel operating X-ray machines need to take? Now, you or I don't often go for X-rays, and we don't often break bones, hopefully. So we're not going to be exposed to huge amounts of this radiation. But a person operating an X-ray machine, a radiographer, would be standing there with the X-ray being all the time, on a daily basis. It's their job. And so they would usually wear an apron that is lined with lead that would stop the X-rays from going any further. Or very often what they do is they position the patient and then they walk outside the room, and the walls or behind a screen, which is also lined with lead, that would protect their bodies against that radiation. Because of course, over a period of time, radiation can be damaging to a person's body, particularly high energy radiation. And so that could be a concern. So, Abram, I think we've done quite a lot in this session, and when we come back, we need to tackle that challenge question. So, over to you.
Well, having said that, Mindsetters, you still have got a chance to still try out and give us your answers, because we'll do the corrections after this break. Welcome back, Mindsetters. Now, I told you that all you need to do to enter for our competition to win this awesome Casio calculator, it is to submit the right answers on the Test Yourself form that is given on Facebook. Otherwise, the notes are there to download or to view. So for now, what are we doing, Tracy?
So I want to answer that question quickly that came up on Facebook. I didn't skip the question. This was, what is the penetrating ability? They can penetrate through skin and muscle, but not through bone. So quite deep, but not through bone.
Thank you. There was a
Pleasure.
question actually from Onkemete saying, I think the teacher just jumped question 2D.
We hope to be listening. Brilliant. I really love the fact that you're interacting and asking questions. It's so important because if there's anything you don't understand, we need to cover that. Let's go across to the challenge question next. So, a roving lunar module, so this lunar module is checking out the surface of the moon, communicates with a NASA spacecraft orbiting at 8,000 kilometers above the surface of the moon. The lunar module emits a pulse lasting 5 seconds once every 15 seconds. So there it's got its little pulse going, but it goes bleep for 5 seconds, and then waits for a moment, and then again. The frequency of the pulse changes from a low frequency to a high frequency. So frequency is changing, okay, from originally low all the way through to a high frequency, and it's changing continuously. How long would it take the radio pulse to travel from the lunar module to the receiver of the spacecraft? So I'm going to draw this picture because I ask you to draw it always. I think it's incredibly important to draw things because what you do is you're then going to be able to identify and see things quite easily, or a lot more easily, I should say. So that's the surface of my moon, okay? And I can draw little craters on the moon. And maybe we've got, there's my little roving lunar module. And up at the top here is the NASA spacecraft, okay? And it's trying to detect these impulses that are coming through to it. And that height is 8,000 kilometers, okay? Now, important to note, 8,000 kilometers, we're going to be always working in SI units, so we need to convert the kilometers to meters. So immediately, I'm going to write this equal to 8,000 times 10 to the power of 3 meters. Now, absolutely, you could go and multiply that out, but I'm going to just substitute it in because I like working with scientific notation, and that's very helpful. What else? How long would it take for the radio pulse to travel? So I'm trying to work out a time value. How long would it take? That's going to referring to time. So what have I got so far? I've got delta x, because that's the distance. I have got not much else. Well, what information do I have? It's not stated, but it is implied. And so we need to go and think, don't just leave it. It's a radio pulse. And what do we note is that it would be traveling at the constant speed, which is c, the speed of light, 3 times 10 to the power of 8 meters per second. And I specifically chose this question or designed this question because I'm thinking out of space. There's not going to be much atmosphere that could slow that down. So I have got enough information. What do I work with? I need to say, okay, so my equation is velocity is equal to the distance over the time. Think about, we're traveling kilometers per hour. We want to work things in meters per second. It's always going to be a distance over time to give you a speed. And I'm writing v for velocity, but in this case it's exactly the same. And I'm trying to solve for time. So I'm taking that to the other side. Change in x over change in t. Oh, sorry, change in t I've already had. It's it's the velocity, average velocity. So over v. Now I can substitute values in. Change in x would be, well, the 8,000 times 10 to the power of 3. Because remember, it was 8,000 kilometers, so it's quite a far distance. The velocity was 3 times 10 to the power of 8 meters in every second, which is a huge number. Going across to my calculator, I substitute 8,000 times 10 to the button, and it's times 10 to the power of 3, and that whole thing is divided by 3 times 10 to the power of 8. Get my answer. We don't ever write our answers as fractions, we write our answers as decimals, And I would like 2 decimal places, I think, in this. It would be a valuable number to give. So 0.02. 6, which means I need to round up, so 0.03. 0.03 seconds is the time that it takes for the radio wave to get from the lunar spacecraft up to this this NASA spacecraft at the top. And that's how they would be communicating, okay, sending information. So the radio wave is traveling very, very quickly. It's traveling at 3 times 10 to the power of 8 meters per second, so 300 million meters in every second. And that's why it can cover that distance of 8,000 kilometers very quickly in this short space of time, 0.03 seconds. Happy with that? Let's keep going. Suggest why the lunar module emits pulses of different frequencies. So it might emit radio waves, and then it could also emit all the way through, maybe it's microwaves, etc. Why would that be useful? Well, you need to consider that there will be a number of different detectors on this spacecraft. And so my answer here is that there will be different detecting devices on the spacecraft. And I mean, this thing has come all the way from the Earth, and so if, maybe the radio spacecraft, if maybe the radio wave detector wasn't working, they would still be able to communicate if other detectors were working. So it would be very important that there are a variety of detecting devices and that they can still be in communication. If one fails, there will be others. And they would be able to pass information along through those different links. Okay, so suggest why the lunar module emits pulses of different frequencies, because there would be different detecting devices. Would there be any difference in the time that it takes a high-frequency pulse to travel compared to a low-frequency pulse? Oh, this is an interesting question, because most of you are thinking, well, of course high frequency is going to travel faster. Think about it. Is that true? Well, you're thinking about this in terms of electromagnetic radiation. And what was our first comment with regards to the properties of electromagnetic radiation? Let's go back and find it. So think about that. Will there be different times, a difference in the times, I should say, from high frequency or low frequency? So I'm jumping back through our slides, and I'm jumping across to the summary. And one of the properties, the first property actually that we've discussed, is that all electromagnetic radiation travels at a constant speed of 3 times 10 to the power of 8 meters per second. So, is there going to be a difference? Well, if the high frequency is traveling at 3 times 10 to the power of 8 meters per second, and the low frequency is traveling at 3 times 10 to the power of 8 meters per second, that's a mouthful. They're both traveling at the same speed. So, no, there won't be a difference, because they're covering the same distance in the same amount of time. They will be traveling at the same speed, so absolutely not. They will definitely reach there at the same time. So let's make sure we get that answer down. I'm going to jump across, see right at the bottom, and say no. So let's go there. No, and this was, oopsie, for C. No, they all EM radiation travels at a constant speed of 3 times 10 to the power of 8 meters per second in a vacuum. So therefore, whether it's high frequency or low frequency, it doesn't matter. It will all be traveling at the same speed. Have we handled that question? I think we have. Would there be any difference in the time for high frequency or compared to low frequency? No, there absolutely would not be. All EM radiation travels at a constant speed, and so you should be happy with that. I'm sure there's some questions on our Facebook page.
Plenty of them.
Brilliant. Abram, over to you.
Cool. The first one, I think it is a basic one. Khotlelelo says, Abram, can you please ask Tracy to give me a simplified version or definition of electromagnetic radiation?
Okay. It's a range of radiation from radio waves, or beyond radio waves, but that all travels at the same speed. If I jump back to my summary, I probably have a better definition. Electromagnetic spectrum is a range of radiation from, you could describe from radio waves through to gamma rays, with a range of uses, but all made up of changing electric and magnetic fields. So hopefully that helps.
I hope that helps too. Here's another one. How are electromagnetic waves generated?
Okay, very important. We did mention this towards the beginning. They're generated by setting up either a changing magnetic field or a changing electric field. So you could choose either. The simplest is to generate a changing electric field to start. So if you can move a charged particle, that's going to be a changing magnetic field. Because if you think about it, every little charged particle has an electric field around it, and if you move that charged particle, cause it to accelerate, it's going to have a changing electric field around it, which would then stimulate a changing or induce a changing magnetic field. And the changing magnetic field sets up a changing electric field. And so that's how it's generated. So it starts with causing a charged particle to be accelerated, which sets up a changing electric field and induces a changing magnetic field continuously. Yeah.
All right, thanks Palisa Makuru for that question. Here's Mishak saying, where do electromagnetic waves transmit energy?
Where?
Yes.
Well, I guess it depends on where they're pointed to. So certainly they would transmit energy to whatever they hit, whatever they're penetrating. So you sit outside in the sun on a winter's day and your back starts to feel nice and warm. That's because electromagnetic radiation from the sun is reaching your back and warming the tissue, transferring that electromagnetic radiation, that energy, radiant energy, into heat energy on your skin. So certainly it depends on what the substance is that it's hitting into, I guess.
Awesome.
Yeah.
Okay, Young K says, what is a lunar module?
Oh, so the lunar module might be a challenging word. Lunar is referring to the moon. So it's a lunar module is this little roving device that the NASA space astronauts have put up on the moon that is going to be going checking out the surface of the moon. We could speak about a Mars rover or a lunar module rover. But basically it's going and maybe it's detecting samples from the surface of a different planet or the surface of some kind of planetary body. So that lunar module was, if I go across to my little picture here, that was on the surface of the moon, checking out the surface of the moon and then communicating back to its to the NASA spacecraft that put it there, probably.
All right, awesome. Let's move on. Another question from Prudence. I wanted to ask if the spectrum will always be in the order shown earlier in the lesson.
Okay. Well, in terms of this order, that is the range of radiation, and that is the order in which it is found. But I mean, I could go backwards. I could go from gamma rays down to radio waves. So no, it doesn't necessarily have to be asked in a question. You could be asked to order it correctly in a question, I guess. But in terms of this range, Gamma rays have high energy, high frequency, very short wavelength, as opposed to X-rays, which have a slightly greater wavelength, so longer wavelength and lower frequency, and so you would go down. So yes, it is arranged in that order. Yes, it is.
Awesome. While talking about gamma rays, Apio is asking, is there any other radiation after gamma rays?
There is, if we can detect it. Theoretically, it's a continuous spectrum, and so we don't, I don't think, have the technology to detect beyond the scope of this. But theoretically, it's infinite. So yes, hopefully. I need to sign off for now. Mindset is, I think it's been wonderful to spend some time with you, and I hope you've learned a lot. Thank you so much for all your wonderful congratulations. I really appreciate it. And I will see you next week.
Thank you so much, Tracy. And just to top it off, I know we're out of time, but I just need to read out this message. It's from Bevan saying, Tracy's an awesome physics teacher. There is so much work we have not yet done, but she makes physics fun. Thank you so much, Tracy. And thank you to Mindset for bringing her onto the show. Sorry for not posting the answer, as we are not done. We're not done with this work yet, but I'm sure that by the end of this show, I'll be done. So thank you so much, Bevan, for that. And thank you, Tracy.
Thank you, Bevan. That's so awesome.
Thanks to all of you Mindsetters for tuning in. We love you and peace.